Molecular dynamics trajectories often contain immense amounts of data and are impractical to manually analyze. We present MolSieve, a visual analytic system which makes it easy to extract insight from these datasets. This is accomplished using a powerful data reduction scheme. Trajectories can be modeled as sequences of states, snapshots of the atomic configuration of the system at each time step. States are often repeated numerous times throughout a trajectory, since low-energy transitions to structurally similar states occur more often than high-energy drastic shifts. We take advantage of this property by first clustering the trajectory with pair-on cluster-cluster analysis, a well-known method to cluster together kinetically linked states. PCCA returns a cluster membership probability for each state. By using a threshold defined by the analyst, we split trajectories into superstates and transition regions based on their maximum cluster membership probability. These two types of regions directly map to the visual components of our system. To accommodate a wide variety of analyses, experts can define properties they want to calculate for each state by providing Python scripts. MolSieve will then automatically execute them and use their results to guide analysts. To study a trajectory in MolSieve, analysts first set two exploratory parameters, the PCCA clustering range and the simplification threshold. MolSieve will return an optimal PCCA clustering within that range. Then, it will use the clustering and simplification threshold to separate the trajectory into transition regions and superstates. We will demonstrate how MolSieve can be used to understand how the structure of a nanoparticle evolves when subject to 750 degrees Kelvin. This simulation consists of over 18 million time steps, which makes it difficult to manually analyze. The timeline view shows that the simulation spends most of its time in the teal cluster, briefly switching to the red cluster before going back to teal. The red cluster is interesting, so they decide to zoom into it using a brush, which updates the other views. The analyst double-clicks to zoom into the timeline view. The rectangles outlined with a dash represent transition regions, and the rectangles without any outline represent superstates. A control chart within a transition region view indicates that the common neighbor analysis ICO count is changing. The orange regions within the control chart represent where averages are falling below the lower control limit, and the blue regions represent where averages are above the control limit. It seems that the superstates are not separated about this change, so the analyst changes the PCCA cluster count to 4. This reveals a transition from a teal to a green superstate, describing that exact change. The analyst clicks the superstates to see their characteristic states in the state detail widget. They also change the 3D render to highlight the CNA counts, which reveal a clear change between the two regions. The nanoparticle loses 2 FCC atoms, colored green, and gains an ICO atom, colored yellow, which is behind this red one. They zoom further into the region between the two superstates. There seem to be 2 regions where the ICO count of the nanoparticle sharply rises, which is concerning. The analyst double-clicks the transition region to expand it several times. This is to ensure that the transitions they see within this region are not just accidental temporary movements. Expanding the region confirms that the system suddenly gains an ICO atom and keeps it. The region where it loses it temporarily is not of interest to the analyst, because that is a stochastic movement. They also adjust the moving average time period. Using the selection button, they select the first region to view it in the corresponding subsequence component. This component shows an overview of the selection and a detailed pixel plot of the states within. Clicking through the states does in fact reveal a change where the nanoparticle loses 2 FCC atoms and gains an ICO atom. Using MolSieve, our expert was able to effortlessly find the exact states that correspond to a structural change within an 18 million time step simulation. Now the analyst wants to find a similar transition in a nanoparticle simulation that has a slightly higher temperature. The simplification algorithm hasn't been able to find any transition regions, probably because its threshold was initially set too low. However, the analyst sees that a large pink cluster splits the 2 major purple clusters of the trajectory, and it describes a movement also involving ICO atoms. They increase the simplification threshold using the Reconfigure Parameters button to see what transition regions are found within that portion of the trajectory. There is a lot of activity within this region of the trajectory, so the analyst uses the Find Similar Regions button and clicks the transition region they found in the previous simulation they studied. The tooltips rendered on the timeline view show that the regions on the right seem to have similarities with the region that they selected. So, they zoom in to get a closer look. There seem to be a few regions which express the same gain of an icoatom. The analyst uses the Compare Regions button to compare the distributions of the superstates with the one they found on top. The leftmost pink superstate has a similar distribution to the teal one. The other two superstates are also comparable to the original transition, but are not nearly as close as this one. Remarkably, clicking the leftmost superstate reveals that it shares the original transition's initial characteristic state. Moreover, the superstate on the right has a characteristic state that is a rotation of the rightmost one we found originally. Intrigued, the analyst zooms in even further to view just the transition between those two superstates. The analyst clicks the state clustering button to see how the states group together structurally. The resulting color scheme of the state space charts assures the analyst that these regions are similar. Then, they select the region where they suspect there is a transition. The subsequence component shows that the nanoparticle is losing 2 FCC atoms and gaining an icoatom, just like in the previous transition they found. The analyst uses the Compare Regions button to compare the two selections. This shows a heat map of the similarities between the two subsequences. Clicking on the darkest rectangles within the heat map shows that the transition is a rotational analog of the first one the analyst found. This concludes our case study and demonstrates that MolSieve can find regions of interest between two huge trajectories within a few minutes.